we're not going to do a normal style warm-up, but here is a Slido. Feel free to answer. It's just asking you about your feelings for the exam on Friday. So throw in some things in there and we'll all look at it maybe after I go through announcements. And then today, I know Monday was like all theory, no fun. But today is all fun, very little theory, I promise. Okay, but just some quick announcements. So reminder, there is a final exam review here in this room after lecture, so you could just stay where you're at. And the TAs are going to go over the practice final. Also, I believe it was officially posted to Ed, but there should be a final section review survey, just like we did before the midterm. If you fill it out, that'll give your TAs a little bit of help in planning tomorrow, specifically around the types of topics you want to have discussed. So you get review today, you get review in section tomorrow. Of course, you're welcome to come to office hours or post on Ed if you have any final review questions. And then to take our brains, I know you're probably all thinking about the final exam right now. So it's not fun for me to do that whole thing where it's like, but don't neglect your other homework. But y'all, don't neglect your other homework, because P4, we did give you an extended period of time because I truly think that it takes you an extended period of time to do P4. So one, if you haven't started P4 at all, please, dear God, start it. You are getting to threat level midnight if you have not started P4 yet. If you have started P4, which I know a lot of you have, like I see you at office hours, I see you doing the work, I appreciate you. If you haven't gotten to the seam carving section, that is probably the section where you're gonna have the most questions that would be helpful to discuss in person with a TA. And I feel like I should tell you now, we are not doing office hours over finals week. As you can imagine, our TAs are also students that need to like prepare for their own finals and all that good stuff. So our office hours will officially shut down on the last day of the quarter. Now, I could have made your homework due that day, but I decided instead, since it's auto-graded, I'll just make your homework due the last possible day I can accept things. So it's like I just gave you all extra late days, no problem. But this does mean that if in your head you're thinking, I'll get around to P4 during finals week, there will be no office hours during that time. You can still post on the Ed board, but like I said, the TAs are also taking their own finals and doing stuff like that. So please, this is my plea to plan ahead in your P4 work. Also, because again, the TAs are wonderful, a set of our TAs went through and they actually made a walkthrough video that tries to give you a more detailed explanation of P4 as a whole. And I think the section that talks about seam carving is especially helpful. So if you haven't read the seam carving section yet, please, dear God, go read it. Go watch that video. At least make some questions for yourself and try and come into office hours sometime between now and a week from Friday so that you can actually talk it through with somebody. Also, just as a reminder, you cannot use any late days on P4. Again, just because I made the due date literally the last possible day. So I need everything from you in order to make your grades by Wednesday of finals week. So plan accordingly. And then fun thing, because I know you had amazing TAs, because of course we have amazing TAs. There's actually this sort of like TA award specific through our CSE department that actually means like a lot to our TAs. It's called the Bob Bandis Award. I'm gonna make an Ed post, but if you had a TA that really helped you out this quarter or you thought went above and beyond, throwing down a nomination for them like really makes a difference. So if I said this and somebody's name or face popped into your head as I was saying it, go put it in this form. It takes like 2 seconds, I promise. Does anyone have any course administrative questions at this time? Should we do a vibe check on this Slido? Let's see. All right. Okay. All right. Oh, horrified. That one's evocative. Yeah. Ooh, look at somebody's got light work. All right. Okay, I see you out here. I like the confidence game. Bad. Correct. I get it. Mixed feelings. Cool. I was hoping that we would maybe feel slightly more optimistic after those midterm grades shook out the way that they did. No? Exams just suck? School is just dehumanizing and resolving all of your incredibly complex thoughts down to a single double is a stupid thing that this stupid capitalistic society makes us do? Ridiculous. But I'm still going to give you the exam on Friday anyway, because like we're all here in the system together. So I feel your pain. Sorry. Cool. Love it. Look, we have like the most votes too that we've had in a minute. Love it. Okay, let's see. We also have some questions. I'll take a peek. Okay. Is dynamic programming a possible final exam topic? I will tell you right now, no, there's no dynamic programming on the final exam. I think that would be unfair. Just like there's no PNP on the final exam. Also, if you took a look at, if you have not looked at exercise 7 yet, you should look at exercise 7. It is all auto-graded. It is intended to reward you for attending these lectures, not to tax you on top of all the other things that we've already given you this week. Will there be a recording of the exam review? Unfortunately not. Technically, we didn't reserve this room, so we're kind of squatting, and squatters apparently don't get Panopto rights. So, sorry, there's not going to be a recording of the final review. But go to section tomorrow and ask your TA to go over the problems you want to go to. How will today's review be different from tomorrow's section? Totally. So my plan, I believe Parker is in the back there, is going to go over the practice final, right? Is that the plan? Yes. And tomorrow in section, your TAs can go over whatever you ask them to go over based on the survey. So if you're like, I really specifically want to talk about sorting, well, you could ask that, fill out your form, and maybe your TAs will pull a bunch of sorting practice problems from exercises or from other section problems or from past final exams, things like that. But the one that's going to happen here in this room is specifically going over that practice final that our other wonderful TAs wrote specifically to help you prepare for this exact final. Great. Oh, are regrade requests for midterm resub still open? To Thursday, yes. One more day, yes. So you got one more day to submit midterm resubmission regrades. Dear God, okay. Cool, great. Feel free to ask any other questions as we go along. I know the TAs will keep an eye on the Slido. But let's dive in to our stuff for today because we get to some very fun stuff at the end. Okay. All right, like I said, today's topic is the P versus NP mystery, sometimes known as the largest unsolved problem in computer science. Okay, so a very brief history of this thing we call computer science. So technically, computer science is a field of research that looks into how we can leverage things we define as computers to solve human problems. And in fact, computer science by definition has existed well before the first electric computer ever existed. Because computers, as we think of them as these like boxes with transistors and stuff inside them, are all just fancy versions of sort of mathematical calculating machines. In fact, the first thing we officially dubbed as a computer was designed by Charles Babbage. He literally just wrote down blueprints for it, and then this incredible generational talent, Ada Countess of Lovelace, but they forget the Countess part, and we just use it as her last name now. She just looked at these blueprints and was like, wow, this machine was designed specifically to solve Bernoulli's numbers. They didn't even build the machine. She's just looking at blueprints. And she's like, I wonder if we can adapt this machine to calculate other things for us. And then she took, frankly, this very boring man, Charles Babbage's original blueprint, and she added something called notes in Notes, which is 4 or 5 times longer than the blueprints, she not only translates everything that Charles Babbage does into like 3 different languages, because she was fluent in like 4 languages, but she also invents recursion, invents AI, talks about modularization, and comes to the conclusion that computer science is about the art of how we translate the complex human brain into something that these computation vehicles can use. That was 1848. That's considered the first ever computer program, because she actually did walk through and invent specifically how you would turn the knobs and the dials on that blueprint to spit out Bernoulli's numbers without ever even touching the machine. And like in the 1990s, for funsies, somebody actually built the machine and then put Ada's program into it, and it worked except for one off-by-one bug. Incredible. I give you that backstory because that's where we start. It's all about how we take the complexity of our human problems and how we translate them to this incredible tool we've created, the computer. In 1948, we started to invent electric computers, where instead of like switches and knobs and things like that, we actually had an electric switch that would move a lot faster. And the faster you can switch between off and on, the more calculations you can do. And so that, frankly, was funded by the government, specifically during the World War II era, so you can imagine what it was used to calculate, but it was essentially used to make what was previously limited to hand calculations, math, trajectories, things of that nature, now automatable. The computer that would have taken up this entire room would have been able to do much more limited math than the computer or the calculator app on your phone can currently do. The phones in your pockets right now are super, super, super computers by the 1940s definition. By the 1960s, we're sort of coming out of the war era, and people are starting to think about this field of computer science and how we can take all the other problems, maybe that aren't just about killing rival nations, and figure out how the computer can help us with those. And so all over the world, researchers started to look around them and ask, what problems can computers solve? And some, they found out solutions pretty fast. But some, they were really struggling to find solutions. And they were all sort of struggling in isolation. And so in the late 60s, early 70s, they started to think about how to group the problems. Some problems clearly fell into a group that was like, wow, computers can solve these really fast, really efficiently, really predictably, no matter how big the number you're multiplying. Even as the number gets really, really big, computers seem to be able to handle multiplication, division, subtraction. But like on the other side of things, the traveling salesman, that idea of, can I leave my house, make all of the stops I need to make, and return back in the most efficient way possible? We just could not find a way to translate that to something a computer could do efficiently. And so was born the field of research specifically around complexity analysis. We've been using complexity analysis all along. Whenever I'm talking about like the linear complexity class, the quadratic complexity class, n log n, all of those things, that was birthed in the 70s specifically to help researchers figure out what is a hard problem and what's not. So, this is more just descriptions of what I've said. Now we are going to start to talk about some of these complexity classes that they invented in the 70s, but we're going to start with the ones that we've already been using. So far, you've mostly encountered what we would call, big air quotes, efficient algorithms. And for our purposes, when I say efficient, I mean essentially like can be executed by current day computers up to an infinite size of n. And so when we actually look at the strength of individual computers and we actually clock the time, that turns out to be anything in the polynomial or P class. And that is anything that is bounded by n to the k. So linear, logarithmic, n log n, n squared, n cubed, n to the fourth, all of that is all in what we would call the P or polynomial time class, which are things that right now with the type of computers we have today, we could find a solution in an amount of time that is reasonable to spend waiting for a solution to get spit out by the computer. Now, we're using this as a bar. We're going to continue along in theory. And you might be like, Casey, but wouldn't like n to the million really take a long time? Yes, it would. Yes, it absolutely would. And maybe n to the million or billion actually isn't something that would execute in time. But if you have an algorithm that's running an n to the million, how many nested for loops have you got? That's not a good time. Maybe re-examine your algorithm. So that's kind of like an edge case of the polynomial time class, but I'm mostly talking about things that are in that sort of like n to the 10, n to the 9, n to the 8, n log n, logarithmic, all of that stuff we're going to sort of mash together in what we're now officially going to refer to as the P complexity class. Here's some actual numbers to help you. So like we have seen some inefficient things. For example, recursive backtracking, or even like, remember when we did dynamic programming, that first recursive Fibonacci? Those are pieces of code you've probably written. Those are not polynomial time things. Those are exponential time things. So the recursive Fibonacci, we consider that to run in 2 to the n time, which is exponential time. If we ran that with an n of 10, we actually kind of get milliseconds, maybe a couple seconds of time. So we could calculate the recursive Fibonacci to 10, no problem. But actually, if we even just increase n to, say, 100, the growth rate of the time it takes for that to execute, remember when we first saw those complexity classes and that one goes, woo, right off the top of the graph? 2 to the 100 would take 300 quintillion years to calculate using the fastest computers we have available to us today. If 300 quintillion years has no meaning to you, that is longer than all of projected time as it currently stands. That's like from Big Bang onward. That is longer. That is why we consider 2 to the n not efficient, because once we get to a size of n that's actually not that big, like 100 and onward, you could imagine having a size that's just not really calculable with our current set of computers. And in fact, if you want to look at it, here's a table specifically from like the discrete math textbook about how long it takes things. And you can see, you know, when n is 10, look, we can run everything in a matter of seconds, even n factorial, which is the worst complexity class, right? But 10 squared, you can see even there at 100, we're starting to get years, right? And then after that, they just stop calculating it. So this is why, even though we've used a couple exponential things, once we get out into the non-academic world, scale starts to make these types of solutions just no longer efficient for computers. Also why dynamic programming is so helpful, because that takes us from that exponential time down to linear time. Whew, so helpful. Okay. So now let's talk about how do we think about problems. One aside, one thing we are going to do is we're always thinking about how we can translate problems into a way a computer can understand. I'm now going to exclusively be talking about something we're going to refer to as decision problems. That's where I take any problem and just reformat it into a yes or no question. Because computers can't understand a lot of nuance, so we try to formulate our questions into yes or no questions. So for example, instead of like find the shortest path, I would say, is there a shortest path from S to T, yes or no? So I'm just saying that words, you know that decision problems, that's just another aspect of how computer science researchers are trying to take complex human questions and break it down in a way computers can understand. Okay. So we talked about the P polynomial complexity class, but all those 1970s researchers, they were like, well, look, here's all of these things we're finding polynomial solutions for, but there's all these other things that feel like they should have an efficient solution. And they feel like they should have an efficient solution because once I have a solution, it's so obvious, it's so quick and easy to verify that it feels like, well, once I have it and I see it and it's such an elegant and simple and easily verifiable solution, there must be something efficient to get there. For example, Sudoku. If I gave you a Sudoku 3x3 grid or 9x9 grid is how those things go, right? And I asked you, is this a valid solution? You could kind of go through and make sure that it satisfies all the requirements. It's like 1 through 9 in each row, in each column, in each like sort of quadrant or whatever. But if I asked you to fill in a Sudoku puzzle, well, right now, I will tell you, computer scientists actually do not have an efficient way to do that. We kind of don't have any way to program Sudoku other than trying everything, like try all the permutations and see which one works. But every time we get into the just try everything, that's when we get to that permutations exponential complexity class, that recursive backtracking. So in the 70s, the computer science researchers were like, well, if I give you the answer to a puzzle and you can quickly tell me if it's right or wrong, it feels like maybe that's a good candidate to research to see if there exists an efficient way to find the solution, not just to verify the solution. Like if we can get to such a succinct and clear and like computer understandable solution at the end, maybe the journey there can also be discovered to be equally as simple and efficient. So they decided to take all of the problems and make another complexity class that they call NP, which stands for non-deterministic polynomial time. They're terrible names. It's math stuff. I know polynomial literally just means many names. I don't know. But P is the set of things that we can solve efficiently, and NP is the set of things where we can verify efficiently. For example, the minimum spanning tree. Is there a spanning tree of graph G of weight at most K? So not even like the smallest, but just like, does there exist a spanning tree that's overall some weight is under this? Well, if I gave you that spanning tree, meaning I just gave you the solution, you could go through and you could sum up all the edges and you'd be like, yeah, it is either under or over K. And so the act of summing up edges and verifying whether or not I've solved this feels very like simple to resolve. Two coloring, that's that like thing we did on Monday with the red and the blue where you've got to have like different colored vertices on the either end of each edge. Well, hopefully on Monday you vaguely remember that I showed you it's a reduction of 2-sat, and 2-sat can be solved with strongly connected components and topo sort. So we know we can solve 2-sat in P polynomial time, but also if I just like gave you a graph and it was already colored, it would be, quote, simple to go through and check, like, hey, does this satisfy that requirement where each vertex has to be a different color on either side of the edge? So these are in the NP problem set. This is about once you already have the solution. So what is this P versus NP conundrum? It is the question that just because a problem's solution can be simply or efficiently verified, does that mean there also exists or a simple or efficient way to find that solution? Meaning, does recognizing that a solution is valid in a simple or efficient time frame mean there must exist a simple or predictably efficient way to find that solution? If you can apply a simple algorithm to verify it, can you apply a simple algorithm to find it? That is the question of the day. Let's think about it in terms of these complexity classes. So the gold dot is the P set of problems. So we've met a bunch of them: multiplication, two-color, sorting, minimum spanning trees, maze solvers, because they use Dijkstra's. All of that is in P polynomial efficient time. Computers are great at it. You could ask it to do mazes that are really big, and computers could still find an efficient solution because Dijkstra's runs in that V log V E log E runtime, which is in that polynomial time. 2-sat, we learned on Monday, exists in this polynomial class. Now, because we can find the solutions in this efficient manner, that means they also exist in the larger and encompassing complexity class of NP. But there are things that exist in NP that we're not sure exist in P. For example, that traveling salesman problem. If I gave you the Hamiltonian route is what is another term for it, the actual, like, I leave this place, I go to all the other places I need to hit up, and I return back as efficiently as possible. If I give you the route, you can check and you'd be like, oh yeah, that's under this distance. But right now, we do not have a way to find that route other than just permutations or some human intelligence making some assumptions or jumping to conclusions or trial and error. There's no computer programmable way better than just try everything. And then we also have some problems, the exponential problems, that after a lot of research, computer scientists have decided there will never exist a computer that is strong enough to resolve it. For example, is the chess move I just made the best possible chess move that I could have made? Because chessboards are so big and all of the pawns and everything move in so many different ways, there's so many permutations to check that actually we have, as the field of computer research, decided we will never be able to build a computer strong enough to verify if your last chess move was the absolute most optimal possible chess move. So that's outside of any of this. We can't even verify it in NP time. But the other ones, I kind of like to think of them almost as puzzles. Like if I show you the solution to a puzzle, you could be like, oh yeah, that puzzle's solved. Now can we figure out if there's an efficient way to solve the puzzle? Question?
Is recursive backtracking outside of everything?
Yes, recursive backtracking would be in the exponential category, yes. For context, recursive backtracking, because you remember it sort of does that thing where like there's a set of choices and in each recursive call, you make the choice and then you recurse and then you unchoose the choice. So recursive backtracking runtime, it's based on how many choices there are. So if you have a lot of things to choose between, but either way, like let's say if it was the knapsack problem, what we did during the dynamic programming one, where we're sort of going item by item and we're either making the it goes in the backpack or it doesn't go in the backpack choice, that's to the n runtime. So recursive backtracking, fully in the exponential category. So, again, the open mystery is P just a subset of NP, or are P and NP the same? Let's talk about how far we've gotten in determining an answer to this great mystery. Okay, so unsurprisingly, this is a pretty big open question, mostly because all those computer scientists in the 70s were like, oh, I'm beating my head against the wall and I can't find a solution to the traveling salesman. Now let me see if I can prove that this is an unprovable problem. As you can imagine, a really good get out of homework free card for these researchers. So, where do we start? Well, it feels like if we're going to prove that something that is NP is also in P, well, like maybe we try to find like the hardest or most complicated NP problem, and if we could prove that one is P, well then maybe by sort of extension a bunch of other ones can be proven as well. And so actually this comes back to this idea of reductions. So once all those computer scientists in isolation were like, my problem's really hard, and then they invented that idea of reductions, how to translate my problem into your problem so I could leverage your algorithm, well, I wonder if there is a sort of shared, we'll say, a shared reduction ancestor. Like, what if there is a way to sort of like take the logic of the other problems and encode them into this one problem so that all of those NP complete problems that have a pretty like somewhat pattern formula to them, like, oh, I see this thing, it's verifiable, it's got a set of requirements, it's got a set of inputs, like do this set of inputs, satisfy these requirements. Does there exist a way to formulate a problem that I could then take all these other really hard problems and reduce them to? Like if there's a way that we sort of can combine all of our logic into like one panacea, if you will, of an algorithm. This is something called NP-complete. NP-complete is this idea of, does there exist a problem in the set of NP problems where all of the other NP problems reduce to it? You can kind of think of this then as like the hardest problem, because it's like, oh, well, if other problems reduce to me, then if I solve me, I solve the other problem. So that's like the hardest one. And so actually, that would mean if you solve this one NP-complete problem, you solve like all of the ones that reduce to it. And so if you actually think about like what kind of problem that would be, it ends up being, could we sort of abstract out just the logic that we're trying to solve in each of these problems? Could we come up with a universal language for how to encode the logic of each of these problems? Wouldn't that be amazing? If we had this sort of like one single universally expressible problem that represents all other problems, could that possibly exist? Something like this. A subsection within the collection of NP problems is the NP-complete complexity class. And so if something can be reduced down from other NP problems, it exists in the NP-complete class. So we think of NP-complete as a subsection of the NP set of problems. Suspense, what do we think? Anybody guess whether one of these exists or not? Does there exist a universal encoded language to articulate all of these NP problems? It does. And in fact, it is referred to as the 3-SAT problem. It was discovered separately by two different people on two different sides of the world in 1971. I will tell you, Cook was in the US and Levin was in the USSR, so they weren't really communicating in 1971, so we give them shared credit. This sentence won Cook, because guess who got the Turing Award for it? The American. The Turing Award in 1971. If a set S of strings is accepted by some non-deterministic Turing machine within polynomial time, then S is P reducible to, and then DNF Technologies is logical sort of encoding. This is the sentence that won the Turing Award, and then he did have a page and a half explaining what this means. But technically what this ended up being then is the language that we saw on Monday, where we have a collection of 3 variables, variable 1, variable 2, and variable 3, and whether or not they are set to true or false is a way to encode the list of requirements that the solutions to all of the NP problems must satisfy. So you can see we've abstracted out everything. We're just now articulating our problems in terms of the logic of a Boolean combination. Yes, question? So 3-SAT is the same family as 2-SAT, as 4-SAT, as 5-SAT, so on and so forth. It's called the satisfaction problem, the satisfiability problem. And so 2-SAT that we learned on Monday, look at how incredibly similar, right? We've literally just added one extra variable. But 2-SAT has a P polynomial time solution like we saw on Monday. However, adding just a third, and then by our friend's question, a fourth or a fifth or continuing on, adds so much extra complexity that as of right now, there is no P solution to 3-SAT. But we have taken all of those other really hard problems that all the researchers were trying to solve, and we've reduced them to 3-SAT. So if we find a solution to 3-SAT, that means we find a solution to literally everything else. Could there possibly be any more of these NP complete problems? Because we can translate a lot of things into 3SAT, but not like everything, right? Well, as it turns out, okay, you can read all these things. By the mid-70s, they had found about 100 more different ways to translate problems in a universal logic encoded language. Karp's theorem in 1972, after seeing the 1971 publish, thought, I wonder if there's other ways I can articulate it. I wonder how many problems I can start to collect together into this NP complete class. How many problems are all just reframings of one another if we abstract out the logic? And so Karp's theorem is that, guess what? There's a lot of NP complete problems. Karp said that in 1972. Nobody believed him. By 1979, they had found at least 300 NP complete problems, 300 different ways to encode the logic of all of these NP problems so that one solution to just one of these 300 problems would solve the other 299 and by extension all of the other problems that you can reduce down into this set of 300 problems. In fact, Gary and Johnson put together a list, this physical book. I have seen this physical book in a bunch of our CSE faculty's shelves. It was a big deal. But after 1979, they could not fit the number of problems into a book anymore. And in fact, now, if you look on research databases, we have thousands and thousands and thousands of these different ways to re-articulate the same logic. So the set of things that would all simultaneously be solved if you solved just one continues to grow. It continues to grow to this day. Last month there was 25 new ones added to the set. So this leaves us with this sort of overarching question. Is there a p polynomial time solution to all of these things? So we've proved that these things are all related to one another. So now at least researchers can tell, hey, if my thing reduces down to one of these NP complete problems, I'm working on an unsolved problem. Actually, a really important thing to be able to know when you are doing research. And also helpful for all of you, if you find yourself realizing the only way I can think to have a computer solve this problem is to try all the permutations, you're going to run out of compute power pretty fast. These are a bunch of examples of how computer scientists have then taken their NP complete problems and just translated them a little bit so that they can get them into the P complexity class just by reframing the terminology. So for example, given a directed graph, report if there is a path from S to T that is at least K. Well, if I want to change it instead to being at most K, that I could solve in P time. So just reformatting how I think about the barriers so that I can take it from an unsolvable problem into a solvable problem. Click. Oh, okay, there we go. Traveling salesman, for example, find a tour that visits every vertex and returns to its start as a minimum walk. Unsolvable as of right now. So how do we translate that into something that's possible? Well, instead of the minimum, let's just pick a boundary and say it's no greater than. We can solve that in P time. Cool. Click, click. Okay, great. So this is sort of ideas okay, now we've sort of hit this unfortunate termination of this logic. We're able to recognize if something's in the NP complete class. As soon as it gets to the NP complete class, you pass it along to a complexity researcher and you move on with your life because your research is probably not going to be successful there. And instead of trying to solve that problem, here are some options. One, maybe you are trying to find the general solution, the traveling salesman is a general solution. Leave one vertex, return back. Maybe you can think about it in a more specific context. What variables, what information do you have about your unique scenario that doesn't make this an impossible problem, but maybe your special scenario is a little bit more solvable. Maybe there's only so many vertices in your particular route or something like that. Maybe it's a special case. You will find that within these NP-complete problems that finding the answer at an infinite n scale is impossible, but sometimes they're really efficient. There's just some special cases within it. Is prime is not an NP-complete problem, but remember how is prime, if I give you a not prime number, if it's divisible by 2, right away I know it's not a prime. That's kind of like a different runtime than, say, if I give you a prime number and you have to actually verify and loop through all of the divisors that it's a prime number. So that's an example of how a special case within the same problem might have a totally different runtime to the solution. So maybe you hedge your bets and you hope you're in a special case situation. Most often what you end up with is approximation algorithms. And so that's what I was mostly showing, where you're sort of translating it into the P terminology. So maybe you can't get an exact answer, but we can get one that's close. That's what we were sort of doing with the traveling salesman. We can't find the minimum one, but maybe we find a weight that we're sort of okay with. Maybe we find, you know, what's the furthest the Amazon delivery truck can travel within a single day or on a single tank of gas or something like that. And I find a loop that exists that is shorter than that, something like that. So that's how most people end up dealing with these NP-complete problems, because life must go on. Even if we can't find the perfect solution, we will find one that's close. Cool. Okay. But we still haven't solved whether or not this conundrum is true. Does P and NP, are they the same complexity class? And so let's talk a little bit about what this actually means in terms of computation in the world around us. I will tell you right now, we all love, it's like the spicy fun thing, like, oh, the greatest unsolved mystery in computer science. Honestly, like 99, I think it's officially 98.9% of computer science researchers are like, yo, P is not the same as NP. We've been trying to find a solution since the 1970s. We can't technically prove it, but a lot of us have the intuition that just because you can verify a solution efficiently does not mean you can solve something efficiently. But the Clay Mathematics Institute in 2010 instituted 10 Millennial Prize contests. There's 10 different unsolved problems in mathematics. They decided they would just put out $1 million prize to anyone anywhere in the world that solved these problems. I think one of them's been solved so far. And P versus NP is on this list. So if you can prove that P is not the same as the NP complexity class, well, at least there you will get $1 million, but actually you'll also definitely win the Turing Award if you can finally put this debate to bed and come up with a formal proof that shows us these two things are not equivalent. Maybe one of you shall, so I don't have to give this lecture anymore. That would be cool. But let's talk about also what happens. Yes, not only would you win the Turing Award, it would be such a massive computer science thing and would put us all to bed that you'd probably rename the Turing Award after you. I mean, what did Alan really do, right? That's ridiculous. He was an incredible genius, thank goodness, and also definitely assassinated by the FBI. That's real. Okay. It's a real story. Okay, let's talk about maybe this theoretical world that, like, we are pretty sure is not the state. But let's pretend for a moment that P actually is the same as NP. So that would mean that anytime you see a solution, any problem whose solution is quick to verify, well, then you can tell a computer to go generate that solution. So maybe the first thing you would do is don't tell anyone that you've cracked this problem. And so you would immediately go grab all of the awards left from the Clay Math Institute, because then what you would do is you would be able to find all of the other remaining open solutions. You would put literally all mathematicians out of work everywhere, because as long as you can verify a math equation, you could solve it. So you just go secretly solve all math everywhere. Take that, math. you think you're the purest science, ha ha ha. You also could essentially decrypt all communication. Right now, passwords, any type of encryption, it takes a piece of information and remember, it hashes it based on some super secret algorithm. So what if P and NP are in the same complexity class? That would mean that if I give you the hash, you could reverse engineer the password every single time. You ever watch in movies or TV shows when they come up on a password and then somebody's like, oh, I know how we'll start, and then they type in 000, and then somebody's like, no, that won't work, permutations, and they all learn that lesson. I don't know why that is such a trope, but you would solve that problem. You could crack every password on the entire face of the planet. Digital money would all be yours. You would end global economy. There would exist no security. There exists no privacy. You would have access to every single system everywhere. No more online shopping, no more online banking, no more online messaging, no more online anything, because the only way we communicate over the internet is that we use the magic of hashing to translate things when we send them out into the dangerous pipes of the internet. Also, you could literally cure cancer. I am totally not the best biologist, but there is this magical thing called protein folding. And right now, we do not have an efficient algorithm for how to generate a protein, but we have a lot of efficient algorithms to verify that a protein exists. If you could solve this, you could generate any protein you needed to solve any illness anywhere. So yes, maybe you could take over all economies all over the face of the planet, decrypt everything, and maybe have access to every nuclear warhead, but you could also cure every illness. So with great power, great responsibility, i.e., a world where P equals NP would be a massively different place than it is now, because we rely on the fact that the act of generating a solution is much more complicated than the act of verifying a solution. Now, like I said, we're all pretty convinced that P is not an NP, and so it is a little bit of a trope to do this for you in class again, knowing that like most people agree. But the reason I show you this is because there's actually something it tells us about the nature of computation that's fundamentally important. What it says is that the act of finding a solution to a problem is not always programmatically possible. That for us as humans, when we find solutions, we do things like take creative leaps. And right now, we cannot program creativity into a machine. Artificial intelligence is not artificial creativity. It's just statistics. That's literally all it is. And so what this means is that artificial intelligence, yes, it may do away with some of the lower brain stuff. Like, let's be real, I know when you've sent me an email that you use ChatGPT to generate because it's bland AF, okay? Like, I get it. We all have access to AI now. But that doesn't mean that the art of articulating human thoughts and feelings and the creative leaps that come with that can suddenly be transformed away by computers. We do not have a way to program creative loops. I kind of like this quote, and most people end with this when you sort of watch these P versus NP debates, from Scott Aronson, an MIT complexity class researcher. If P equaled NP, then the world would be a profoundly different place. There would be no special value in these creative leaps, no fundamental gap between solving a problem and recognizing a solution. Everyone who could appreciate a symphony would be Mozart. Everybody that can follow step-by-step logic would be Gauss. Everybody that could recognize a good investment strategy would be Warren Buffett. But there does exist immense value in those creative leaps, and it is in the mystery of the human brain that those things exist. And if you go all the way back to 1848, that is exactly what Ada, Countess of Lovelace, meant when she said humans will never be replaced by computers, because creativity has a spark and a magic that we have not figured out, that we cannot program. And so at least for right now, that is why you will always be smarter than AI. but I will leave you on one final note. This is all based on computers as they exist now. But there is a new field emerging called quantum computing. And quantum computing, there is no such thing as a quantum computer yet. It has not been invented, but what quantum computing is trying to do is trying to physically recreate the intelligence of a human brain in a computer. We haven't done it, but I don't know. Maybe you'll see it in your lifetime, and then all this will be bunk, and then Skynet will be here, and I will see you along with Sarah O'Connor in, like, I don't know, 30 years ago or something. Cool. All right. Thank you all so much. That's the PNP problem. I put a bunch of YouTube videos in here if you're interested. That should also answer your final questions on your exercise 7. Come back on Friday for our final exam. And then next week, we'll have one final memory lecture, and then the last lecture of the course, I'll do what to take next, what comes after 373, all that fun stuff. Thanks so much, everyone. See you in a bit.